Okay, so we're going to go over some homework problems with the amazing students that I have here with me today.
Woo!
All right, we can kind of hear some of that.
Oh, yay!
Ha! 2a gives you the derivative, and it wants you to sketch the original function. We have talked about you should do that. The scale is different, so it would be better to draw it on a separate graph. I'll do it on top so we can see the connection between the points. But I'm going to do a first derivative and a second derivative sign chart, because that'll help me figure out the shape of the original function. So if I'm looking at this, I've graphed the derivative, so what I'm looking at is what I'm doing a sign chart for, not the slopes of what I'm looking at, but what I'm actually looking at. So where are the zeros of what I'm actually looking at?
1. -3.
Yep. So 1 and -3 are zeros. And then before -3 is the graph, positive or negative? Positive, because it's above the x-axis. And then between -3 and 1, and then bigger than 1. Okay, so that's our first derivative sign chart. Then we do our second derivative sign chart. And for the second derivative, instead of looking at what the function itself that's in front of us, what we want to do is look at the slopes of what's in front of us, because the second derivative is the slope of the first derivative. So we're looking for where the slope of what's in front of us is 0. So where does it look like the slope is 0? That's a little max right there.
-2-ish.
Okay, so right here, which we're going to call -2. Okay, I'm just going to erase these little lines. Okay, and so we're looking at the slope before -2. Is it positive or negative? Negative. And then between -2 and 1?
Positive.
And after 1? Okay, so the top graph is telling me increasing and decreasing of the original function, and the bottom graph is telling me concave up, or sign chart is telling me concave up and concave down. So I just kind of like to write increasing, decreasing, decreasing, and concave down, up, down. And we will, anytime we have a sign change on the second derivative, we'll have a point of inflection. And we have to kind of decide on the first derivative, do I have any relative maxes or mins?
On the first? 1.
Okay, and is it a max or min? So increasing to decreasing is going to be a relative max. Okay, so now I'm going to draw the original function, and when I draw it, remember that where I choose to start is random. It could be up or down from wherever I start. It's just it has to have the same basic shape.
Why is -3 relative?
Because the function is changing from increasing to decreasing. So if you change from increasing to decreasing, then at the top, you would have a relative max. Because that's the first root line test. So I'm not saying that it's a max on what I'm looking at.
Yeah.
I'm saying it's going to be a max in the original function. Okay. And so when I look at this guy, I'll just use purple maybe, I know it's going to be increasing up to an x value of -3. And it also says it's going to be concave down. Okay? And now I could pick anywhere on -3, so any y value, but it's increasing up to -3, an x value of -3. Now you could have drawn that here. You could have drawn it here. And then I get rid of those two. Okay, so you don't know how high or low, you just know that you have to draw a shape that is increasing up to an x value of -3. It's also concave down. Okay. Now, it's going to be decreasing the entire rest of the time. Okay, but it does change concavity. So I can pretty much know the rest of the time I need to go down. Just down, 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 down. Okay, but I'm supposed to continue to be concave down until the x value of -2, which was associated with that point. So I could just go like that. That continues to be a and that's lined up with the relative min there. So that's concave down. Then I'm supposed to change to concave up, but still decreasing, but concave up all the way to 1, an x value of 1. So that's me trying to do the shape to be concave up, and then concave down the rest of the way, but still decreasing. So something like this. Again, as long as you have that shape, it can look different. Yeah.
So as long as the y value for -3 is the highest point and it's really close to that shape, it doesn't matter where the y values are?
That is correct. And I'll tell you kind of where that comes from. So if you think about, I'm going to do it with something simple, but say you had like x squared plus 17, and you took the derivative, be 2x, and you take the second derivative, it'd be 2. Okay? Well, if you think about it, the information, if I had y equals x squared minus 77, I would have the same derivative, and I would have the same second derivative. So I have no way of knowing, without them giving me one y value in the original graph, how high or low it is, because even something that's up 17 or down -77, all I have information about is the shape of the graph from the derivatives, because the derivative of a constant is 0. So if they could give me just 1 point off the original, then I could kind of ground it and know where it was. But other than that, because I don't have an original point, I only know the shape. You draw the same shape up or down, you are also correct.
Interesting. That's weird.
It's a little weird. Kind of weird though.
It makes it easy, but also like weird it's easier.
Yes.
Yes.
Okay, other questions on the drawing stuff? Here's some drawing. Are you looking at their graph compared to our graph?
No, I on 2B, I guess I didn't read the instructions, but I didn't realize I did for A, so I guess I just lost my mind on B. I didn't realize they were starting with the first derivative, so that's fine.
Do I need to work any more on the drawing ones?
I think I can figure it out. Yeah, that works.
Okay. Need more on the drawing ones,
No.
or we're going to regular problems
Not
now?
the drawing one, but
Okay.
I do have a question on the 9.
Let me get rid of this. You think 9 would do better on the whiteboard or paper? Paper?
I really don't care.
And this is 9. This 9?
Yes.
Let's see what we got. That's what you're going to do. So this is 9 on 16D.1. Okay, so it gives you f of x equals e to the x over x. And the first thing it says is, does it have any x or y intercepts? So let's just try to calculate, and that's kind of how we'll know. So for an x-intercept, you would have to let y equal 0. And so if you did that, it would look like 0 equals e to the x over x. And the only way that can equal 0 is if the numerator is equal to 0. Because if the denominator is equal to 0, we undefined. So whenever you have a fraction equal to 0, you just want to see, can the numerator equal 0? Well, when does e to the x equal 0?
Spooky never.
Good answer.
The food drive goes with the words and spooky never.
Awesome. They've caught on to the cool trends that I've started. I was thinking something super cool, of course. Y-intercept, how would you do that? And so you would have y equals e to the 0 over 0. Well, that's 1 over 0, and that's undefined. Okay, so that's also basically a spooky never. So there are no x or y intercepts. Was it all of this one that you had trouble with? It was certain ones.
I got lost after that part.
Discuss f of x as x approaches infinity and negative infinity. Well, I'm just going to grab the look at it. So graph e to the x over x. That's not a shape you would just be expected to know what it looks like. So as you look towards negative infinity, or sorry, positive infinity, does it appear that this is flattening out to any particular value? It seems like it's going to infinity. So what I would say is the limit as x approaches infinity of e of x over x is infinity. Okay, so as we're going towards the right, our function seems to be getting higher and higher and higher. And then as you go towards the left, though, as you approach negative infinity, is the y value flattening out to anything?
Zero.
Yeah. So the limit as x approaches negative infinity is 0. And that is your horizontal asymptote. And so it occurs on the left, not on the right. Okay, so that's B. C says find and classify any stationary points. So that just means find out where the derivative equals 0. So I'm just going to write the problem again. So it'll be on the right side of my paper, but I need the derivative. So what rule am I going to have to use? Quotient rule. So here we go. Low d high is just what? Minus high. What's d low? Over low squared. Okay, so when we do our first derivative sign chart, we want to do where the derivative equals 0 is undefined. It's definitely undefined when x is 0. Set the numerator equal to 0. And do you see anything you could do to help solve that? You got it. And what would that leave me? Perfect. Okay, so you set each factor equal to 0. I think we have a theme today. Let's see the x equals 0. Just consider it a continuation of Halloween. And you get x equals 1. Okay, so when you do a sign chart, they're really only asking you to classify the 1, but you need the 0 because you can still have a sign change in between 0 and 1. So this is a sign chart for f prime of x, which we could do by substituting in points. I'm not going to do that to myself. I'm going to graph the derivative.
Did you have trick-or-treaters?
No. Not have trick-or-treaters, but I never do. Like, I used to try to get my next door neighbor to come over, and well, she used to come over, but then like I would have to ask her to come over, and I don't think, as far as I know, I don't turn the lights on because nobody ever comes. Like, even when I was a kid, because I live in the house I grew up with.
That's really cool.
So, anyways, people didn't really come because I live on Green Gorge and my houses are really far apart. And so everybody would go on Arrow Drive because the houses are really close and it's flat. I mean, we would go up, you know. But I would tell my friends, my mom would always buy like a pack of the full-size Hershey bars, and that was like a big deal back then. And so I'd be like, well, come by my house because my mom will give you a full-size candy bar. And so I'd get like a couple of my friends would come by. But like, we've never had trick-or-treaters much in that house. And plus people tend to go to like the rich neighborhoods and like go through.
We live in Old Town, and I'm like a dead end, so I live 2 houses down from the top of the hill. And kids always like come around, and you can see them and hear them, but like they never come to our house. It's literally 2 houses away from where everyone stops. It's really sad.
I live on one of the first 2 main streets in Brook. So, you got it.
Well,
There's like up my street to the left, there's a cul-de-sac after David Bernier lives, and there's a house further down the cul-de-sac. They would do the exact same things your parents do. They would just buy gigantic candy bars, and whoever would actually make it to their house was going to live in the candy bars.
right.
So I haven't packed them in that house.
Well, my dad, where he lives, they are in like a subdivision. They would get tons of people, so it would be fun. You get to see all the kids in costumes. So plus, most of the years that my kids were growing up, we weren't at the house on Halloween because we would go to a church and do trunk or treat. And so if we weren't at the house, people were really not going to come, you know. So it's just, I don't know, it's just the way it is. We do show this is the first derivative, and it is undefined in So before 0 is the derivative positive or negative. And between 0 and 1, and after 1. Okay. And so what it asked us to do was to define define or classify the stationary point. So there's technically only one stationary point where the derivative equals 0. And so is that guy going to be a relative max or a relative min? Min. So 1 comma something is a relative min. I'll figure out comma something in a second. Because f prime of x changes from negative to positive. Okay, now the comma what, I can go up here and just substitute it into the original. So f of 1 would be e to the 1 over 1, so just e. So it's actually point 1 comma e, which I think is a fabulous point. Haley, what do you think of point 1 comma e? So it's okay? All right, I just wondered. Had something against e or just the derivative. Next it says find the intervals where the function is concave up and concave down in the sketch. And then it wants a tangent line. It's asking a lot of you. Okay, so second derivative. I'm just going to stick it right here under my first derivative so it'll be easier to find. So what rule have I got to do again? I do have to do quotient, and there's a product rule mixed in with it.
Okay, technical question.
Yes.
Would it be easier if we multiply out the e's and the product rule, or do we just leave it like that?
Okay, well this is kind of the one where it is multiplied out, because e to the x is times 1 is just 1. The one where I had it factored would be, so you're either going to have to use product rule here, or if you use this form where we factored, you'd be using product rule on the whole thing. So really the only two choices are if you want to do it from here or from this version of the factored. Or whichever one you like. I'm happy with either one.
I like the first one.
Okay, so we'll stick with that one. Okay, so we're going to do low. Now d high, we're going to have to do some thinking here. Because d high, I got to use product rule on this, and then the derivative of the x is just e to the x. So product rule, first times the derivative of the second, plus the second times the derivative of the first. So that takes care of that, and then the derivative of e to the x is e to the x. And then, so that's, all that was low d high minus high. Oh no, I'm running out of room. Let's do low. It's going to be on another sheet of paper there. All over low squared, what would that be?
Could you do the product rule part again?
Yes. So this was low, and then for d high, I did product rule on this part. So that was, this is first, this is second. First, second. So that's first, derivative of the second, plus the second, derivative of the first.
Okay.
And then I just did minus e to the x, because I was doing derivative separately. So we've got a mess. I'm hoping some of this stuff cancels. We'll check it out. So I can see that inside here, these are going to cancel, e to the x minus e to the x. So really, I could go ahead and multiply these two by each other.
If we don't multiply it, we can just have the negative sign and get rid of those two?
We can't because this is, I got to do the multiplying first. Okay, so we're going to have x cubed e to the x, and then I've got to distribute the minus and the 2 to the x at the same time. So it would be minus 2x squared e to the x, and then plus 2x e to the x. I think we can do x and e to the x. I don't have a 2 in this one. That's okay. So yeah, let's take out the x and e to the x. What would that leave me?
X squared
that's looking better. And so we need to find places where the derivative equals 0 is undefined. It's undefined that x is 0, so it's not going to equal 0 there. We know u of the x is never 0. So we really just need to figure out if that's something that'll factor or not. I a little bit have my doubts. Are there any two numbers that multiply to give you 2 and add to give you negative 2? I don't think so. Another thing we could check real quick just to make sure is the discriminant. So I'm just going to do b squared minus 4ac real quick just to see what's going on. So that would be 4 minus 4 times 1 times 2. So 4 minus 8. So if the discriminant's negative, what does that tell you?
That it's
Okay, well let's think about what the discriminant is. So if you're in the quadratic formula,
Oh, you can't have a negative discriminant.
okay, because so it's imaginary though, right? Because you'd have the square root of negative 4, which is 2i. So this means you have 2 imaginary roots, and that's going to be on your IB test. And so that means that it never crosses the x-axis, so it never equals 0. Okay, so the only spot where we can have a change in concavity, there's no inflection points, because the only spot on the second derivative that we could possibly have is 0. So we need to check to the left and to the right of 0, and I'm just going to graph my second derivative to decide what it is before you could substitute in points. But looks like it might take me a while to substitute in points. So we're going to have x times e to the x times the quantity x squared minus 2x plus 2 all over x equals. Okay, and we thought it was just undefined at 0, which is what we got. We don't have to worry about there being a 0 anywhere where it's right on the line, because we already said it wasn't a 0, so this must just be really close to 0. We could verify with the table, but before 0, positive or negative, and after, positive. Okay, and so this asks us where is it concave up and where is it concave down. So I'm going to say f of x is concave down from negative infinity to 0 because f double prime of x is less than 0, and f of x is concave up from 0 to infinity because f double prime of x is greater than 0. Then it asks me to sketch the graph. It is kind of difficult to sketch the graph given that I only have one point on the entire graph. The only point I got was so basically you combine the first and the second derivative to try to graph what it is, only it's not okay just to get the shape. I'm supposed to actually know where it goes through. I do know that I have a vertical asymptote at x equals 0, because this is the original function. So I know that. I also know that I have, the only point we found was 1 comma e. So that's like around here. That's the literal only point that we got out of all of that stuff. We do know, I need to find my first derivative and my second derivative. It goes together. Before 0, I know that it's decreasing and concave down. So I'm expecting something that's decreasing and concave down, but frankly, I needed a point or something to do it. I do know there's an asymptote. I would kind of be tempted to think it was going like this. But it definitely has to be decreasing and concave down the whole way. In this situation, you might want to try a point. So like If you tried -1, if you really didn't have a calculator to help you, you'd have e to the -1 over -1. So that'd be like -1 over e, which is like -1 over 2.71. Okay, so it's like -1 and then just really, really small negative. So I know that point. So my guess is it's got to be decreasing and concave down. What if we put in a really, really negative point? Like 10, okay. So that would be e to the -10 over -10. So it's going to be -1 over e to the 10. So it's still going to be super small. So I think it's going to go like this. We'll check ourselves in a minute.
And how do we know that there's an asymptote?
I was putting the asymptote at 0 because when we kept putting in, like you told me to do 10, this is an even smaller negative number because I'm dividing by something bigger.
I mean on the y-axis.
Oh, the vertical asymptote? Because it would make the denominator equal to 0 on the... Okay. Alright, and then after that, so let's kind of see what's going on with our first and second derivative after that. It's supposed to be concave up after 0, and it's decreasing and then increasing. So I would say decreasing and then increasing. I don't really know the shape. It could go off that way. It could go straight up. But that's basically what I have. I think that did we graph the original already?
I think so.
So I might already have it.
Where did we?
And that was the first derivative. Okay. So there it is. And that looks like what we have. Again, I really couldn't have gotten the left side without substituting a point because the only point I knew was the relative min. So I mean, this could have literally been high or low without having a point to ground it. Okay. And then the last thing said, find the equation of the tangent line at x equals -1. So if we're looking for some kind of tangent line here, they just want the equation of that. And that really shouldn't be too hard because we've calculated a lot of stuff already. So a tangent line, I said -1, right? We need a point and a slope, and frankly, we already did that. We did it just because I needed it to graph it. We got -1 over e here, and the derivative we have, but we didn't find it at -1. So I'm going to have to show the derivative, which is right here. And I'm going to have to plug in -1. So that would be -1 times e to the -1 minus, leave the minus there, e to the -1 over -1 squared. So I caught a break there because -1 squared is just 1. So I have negative e to the -1 minus e to the -1. So that's -2 e to the -1, which is -2 over e. Yes, no, maybe? Okay, so then you just put it in y minus y1 equals mx minus x1. So y minus -1 over e equals -2 over e, x minus the -1. So you can change those to pluses. And you can distribute if you want. If you do, you'll be able to combine, do a little bit of combining with the 1 over e and the -2 over e you'll get if you distribute. But you are not required to, and that was a long problem, and I'm tired, so I'm not going to do that. Once you plug it into there, you have got it. Haley's thinking something over. Not sure what.
I just don't know if I could have done that.
Yeah, no.
What?
I'm sorry for all those.
Well, not really, because they're
Right.
They should be appreciative to you because
I asked
without you, I
I
wouldn't
asked
have
the
answered any
But
questions.
they would have been confused.
I just would have taught the lesson. I wouldn't do questions. Oh, let's imagine a kid asked a question. I
I
would.
know activity like won't pass the book. You can do it to me.
Sure.
I just do not.
I left my water bottle at home.
So,
Oh my goodness, my mom was all like, she was not fond of me skipping school for senior skip day. That's not why I'm here. Like, she was like not happy. She literally came into the school and she texted me. She's like, "Where's your car, Haley?" And I was like, "Where it always is." And she's like, "I don't see it." I'm like, "Mom, I'm literally sitting in band class. I don't know what you want me to tell you."
oh my goodness. See, then I would feel guilty after that
Yeah.
if I had said that to you. I'm just like,
I think she came to like build it me, so I don't think she was going to like stalk me.
No.
Better.
but while she was here, she might as well check.
Yeah,
right? I understand. But then, if I had said something really hear that, I'd be like, I was just kidding.
So my sister was a senior 3 years ago. My mom did not let her skip on senior skip day, so we were discussing it. And mom said, "Sure, that's fine. Just go to band and maybe math, but like not do like go home the rest of the day. I'll be fine." So Marie just was quite appalled.
I don't blame her. That's what happens.
What? You're letting her?
Okay, so when we take a look at this one, we're looking at the first derivative. So the first thing we want to do is mark the zeros of what we're doing, of what we're actually looking at. So where are the zeros of that function?
-2.
Yeah, so I can tell if they're like saying that little spot is -2, but we're just going to assume that's what they're saying. And that's for. So we have zeros there. And then what is the sign before you get to -2? Is it positive or negative?
Negative.
And then,
Positive.
and then.
Negative.
And then for the second derivative, you're looking at the slopes of the graph that's in front of you. So where is the slope equal to 0?
Like 2. 1. Okay.
Okay, so we're looking for that, and we're guessing 1. That's fine with me. It doesn't really matter. Okay, and so what is the slope prior to 1?
Positive.
And then,
Negative.
and so we want to put these two things together to graph the original function. Okay, and also this is like a quadratic, so the original I would expect to cube it and have two terms. And the two terms you can also see because we have two spots here. So we know we're going to be decreasing, 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 basically. And so all the way up to -2, we're going to be decreasing. So I'm going to, and also concave up. So I'm going to go kind of like that. And then I'm increasing all the way to a value of 4. So I'm just going to put a random place I want to try to get to. I'm going to be increasing the whole time. But I do need to change between concave up and concave down at 1. So this will be the rest of the concave up, and then I'll switch to concave down. It's supposed to be connected. And the rest of the time, I'm supposed to still be concave down and decreasing because of the negative here. So it could look something like this. Again, the same basic shape that can be up right here. So we have homework.
That makes more sense.
And now we're going to move on to the lesson. It's not too long a lesson.
No. Okay. Is it a continuum of the lesson of the other day?
No, it's new. And in fact, I have your CLT on the board ready for you. I can calculate the average instantaneous velocity and acceleration. Physics.
I had to do 3-dimensional velocity for a heart yesterday, and I was not excited about it.
For a heart? That sounds really
Yeah,
cool.
it was kind of cool, but like it had these big equations, like it was for the teams thing. They like did big equations, but I didn't know if the variables worked, so I really didn't define it. So like I went forever, and then I kind of realized A meant area, and I was like,
Oh, okay.
what?
That sounds really interesting,
It was
actually.
kind of cool.
We're doing vectors towards the end of this year. We do vectors and statistics. But Dana was like, everything they do has vectors. She's like, they are so important. I was like, okay. So they do a lot of the calculus with vectors and things like that mixed in. Anyhow, it's just sort of interesting. Okay, so these are going to be applications of differential calculus, and so it's more like supposed to be the real world examples. That was kind of what we did before applications, in that I could figure out from the derivatives, instead of just calculating a derivative, at least I was doing something with it. I was identifying the shape of the curves, finding maxes and mins and stuff like that, but that's still kind of just pure math. Okay? And so one of the principal applications is physics for derivatives. And the very simplest thing that you can do is basically motion, which you guys know a fair amount about. But they use S of t to be displacement or the position. If they say displacement, they mean displacement from zero, so it also becomes your position equation. If you take the derivative of that, the rate of change of your position is velocity. Have I told you this part before?
I think so.
Okay.
Potentially.
All right. It's hard to remember sometimes.
Oh, that's what my IA was about.
There you go.
I've read it yet. That's okay.
Yep. Okay, and then if you take the derivative again, so the second derivative of position, or that would just be the first derivative of velocity, then you're going to get acceleration. Okay, and what we're going to do today is just the average velocity and instantaneous velocity, and then average acceleration and instantaneous acceleration. And it's all going to come from the position equation. They're going to give us something like that. But just to kind of talk about it in general, if they give you a position equation like this, S of t equals t minus 2 quantity squared minus 2, what they're trying to tell you in our situation, we're going to compare it just like on a number line. And granted, in physics, you probably don't move on a number line. You probably actually move. But our general equations will look kind of like this. So we have a number line, and we can do what's called a motion diagram that shows you where you are at different times. And so what we would do is just plug in, say, 0, and that would tell us where we were starting at time equals 0. So if I put in 0, I'd get 0 minus 2 squared. Okay, so that would just be 4. Minus 2, I would get 2. So what that would mean is that at time 0, I would start at 2. Okay, so I'm actually going to put that above the axis, and they do that because basically what happens is you start to move back and forth on the number line, and if you move back and forth on the actual number line, it just starts to look like a bunch of scribble. You can't see it unless you draw it above, and we're just in the motion. Now, I actually know where this stuff turns, so if you think about it, and you probably do too, if you think about it, this is a parabola. What's the vertex of that parabola? 2, comma.
0.
It's okay, it's in vertex form though. So if you think about vertex form of a parabola, the h comma k is the
negative 2, negative 2.
Oh.
2, negative 2.
Yes, 2, negative 2, because it's h comma k and the minus is already included. So we usually think of it as being like the opposite of what you see here and then what you actually see out here. Remember that this would move right 2 and down 2. Okay. So what's going to happen is if you think about a parabola and it's an upward parabola, if you graphed it, it's going to look like an upward parabola. So it's going to change directions of its at the vertex or at 2. So the next, oh, go ahead.
Why are 2 negative 2?
I think one of those is supposed to be an equals.
I was so confused.
I don't blame you. That's supposed to be equals 2, because then it was 4 minus 2 equals 2. Yeah, when you only draw half of your equals, the awful thing about that is it's a minus. It's not a good plan.
I want to break the sheet. 0.
Yeah, that's a good question. Okay, so basically the next point I'm going to substitute in is 2, because it's going to go the same direction until the vertex, and that's when it's going to change direction. So I kind of know that ahead of time, but so put in 2. And so you get 0 minus 2, which is negative 2, which shouldn't be a surprise to us because we just said the vertex was 2, negative 2. So what happens is it's going to go to the left until it gets to negative 2, and that's at time equals 2. Now I'm expecting it to change directions because it's a parabola, but I'm just going to put some other random point in, like 3, just because I like small numbers. So 3 minus 2 squared minus 2. So you have 1 minus 2, which is negative 1. So what happens is it turns around, and now it's here. So that's called a motion diagram, and we'll be doing that more. But just to kind of give you the idea that the S of t is telling you where you are at a given time, and that's what you use that equation for.
Why is the time over 2?
Why is the over negative 2?
Yeah, positive.
It should be 0. I don't know why I did that. I think because it was position 2. But yeah, that should definitely been, that's where it was at time 0 and then time 2 and then time 3. Thank you. So that's what that tells you. So if you get a positive S value in your number line, that means you're to the right, and negative would mean you're to the left, if you're talking about motion on the number line. So that's kind of what those signs tell you. And so then the next thing we're going to talk about is velocity. And you can get velocity by the derivative, okay? But they're either going to ask you to find average velocity or instantaneous velocity. If they ask you to find average velocity, that's the same as v bar. So whenever they put a bar over it, it means average. And it's basically, it's this formula, but it's just the change in position over the change in time. This is also the slope of a secant line on a position versus time graph.
So do you think we should write down the delta S over delta T or that?
Either
I
one.
know that's one.
This, but if you just want to write this and not that, that's okay. They're equivalent. So for average velocity, it's the slope of the secant line. For instantaneous velocity, it's the slope of a tangent line. Well, if you think about the slope of a tangent line, you're just moving those 2 points closer and closer together from the secant line. Okay, so if I take 2 points, okay, this is basically change in position over change in time again. Okay, the time's just being t and t plus h. And they're letting that time get closer and closer to 0. That's the slope of the tangent line, which is the derivative. Okay, and so the instantaneous velocity, you don't have to do it from first principles. It's just s prime of t, which is the instantaneous velocity, which is the slope of a tangent line on a position versus time graph.
So instantaneous velocity is S prime.
Correct.
Is that equation 14?
It might help you because they're going to kind of format it like that. It doesn't matter if you can kind of recognize the formula as being the limit definition for S prime of t. But if you don't think you'd recognize it, then it might be good to write it down. So this is telling me to draw a graph of S of t and calculate the average velocity and the instantaneous velocity. And I'm going to graph S of t based on the fact that I realize it's a parabola. And I also kind of already know some points on the parabola because we substituted in 0, 2, and 3. So this is going to be my graph. And we already figured out it had a vertex at 2, negative 2. So this is S of t equals t minus 2 quantity squared minus 2. And we also found 2 other points up here. So we found S of 0, S of 2, and S of 3. So I'm going to put those 3 points on there. So S of 0 was 2. S of 3 was negative 1. And this is a parabola, so you know everything's symmetrical. So I could actually put symmetrical points on each side if I wanted to. Could put one right here. drawn symmetrically. Now it wouldn't make sense really to continue this for negative time, so I'd really, when I graph this, this would be the time. I didn't say any units. Let's just go for some nice SI units. We can do our position in meters.
Is the point one negative ones that you use there?
I did it because it was balanced around this one. So, like this is the axis of symmetry. So if I have a point here, I can reflect it about the axis of symmetry and draw another point. You could just substitute it into the original equation if you want. I just thought it'd make it possibly make my graph look more balanced. So that's my position versus time, and now it says average velocity and instantaneous velocity. I frankly have to give you a time frame for that. So average velocity, we're going to say from time equals 0 to time equals 3. I have to give you that. Instantaneous velocity we'll do at time equals 1. So I do have to give you that. So anytime they ask you for average velocity, that's just going to be change in position over change in time. So that's your position at 3 minus your position at 0 over 3 minus 0. So 3 was one we substituted in. What was our position at 3?
Negative.
And at 0? Okay, and these are technically in meters, and that's in seconds. You don't have to put the units in, but that's what it would be. So you would have negative 3 over 3. So negative 1 meters per second is your average velocity. It's also the slope, so I'm going to draw the slope on there, between 0 and 3. So here's 0, and here's 3. So the slope of this is the average velocity over that time. That's what we just found. When they say instantaneous velocity, that's like the slope of a secant line at t equals 1. So that's going to be like this. What is the slope at that exact second? Not on average, not over some period of time, but tangent line, sorry. Slope of the tangent line at that point. Well, how fast are you going at that exact instant? Not an average over some period of time, but like if you were looking at a speedometer, how fast would you be going? Okay, and so this guy right here is going to be your velocity at 1. Okay, it's also s prime of 1. It's also the slope of a tangent line. Okay. So, you think about it, the difference between average and instantaneous. You go on a trip, you go 200 miles, and it takes you 4 hours. What's your average velocity? 200 miles, it took you 4 hours. What was your average velocity? 50 miles per hour. But when you go on a trip, are you always like exactly on 50 miles per hour? No, you go up and down, up and down. Okay, and so there's a difference between what your speedometer reads and what you do on average, and that's the difference in what we're finding here. How fast our particle or whatever it is going at that second versus what was it that's average over some period of time. And for that, we need the derivative for the instantaneous. So this was our position function. That's what I want to find the derivative of. You've got some choices. You can find the derivative right now because you know power rule and chain rule. Or you can multiply it out and then just take the derivative of each term one at a time. Chain rule. Okay. Let's do it. So s prime of t, talk to me about it. And the derivative inside is just, and the derivative of negative 2? 0. Okay, so that's not too bad. Just distribute 2t, because I don't really need that 1, minus 4. And then I just want to know the velocity at 1, which is the same as s prime of 1. So it'd be 2 times 1 minus 4. So negative 2 meters per second, which seems reasonable based on my graph, because this graph seems steeper negative than the other one. Is that all right? I like it. I like the encouragement. Kind of cool. See what you're missing, people? Kind of cool stuff. Now we're basically going to do the same thing with acceleration. Okay, so if you want average acceleration, which average is always indicated with the bar on top, so average acceleration is basically just the change in velocity over the change in time. So this is the slope of a secant line on a velocity versus time graph. Instead of doing a secant line, you do a tangent line, you can get just what it is at an instant. Okay, so the instantaneous acceleration is just going to be the derivative. Okay, and remember, this is first principles for a derivative. You're basically taking an average and between two different times and letting that time difference get closer and closer to 0. So this is the slope of a tangent line on a velocity versus time graph. So we're just going to do the same thing, only with velocity this time. So you guys already found v of t was 2t minus 4, because that was just the same thing as s prime of t. So that's what I'm going to graph. And I'm going to do the slope of a secant line on it and also the slope of a tangent line. Okay, so we took a brief pause to delete 5,000 things from my computer. / 2 things that were really large files.
Yes.
Okay. That's my power of estimation. I think you should be impressed. Okay, so we're going to graph v of t, and that's just linear. It has a y-intercept of what? And a slope of, okay, so I'm going to go up 2 over 1, up 2 over 1, up 2, make the dot bigger, up 2 over 1. That ought to be pretty good. If I graph my axes, this is time in seconds, and this is velocity in meters per second. So I graphed it. They want average acceleration, which is change in velocity over change in time, between time is 0 and time is 3. So v of 3 minus v of 0 over 3 minus 0. So we need the velocity at 3. So if you plug 3 into this, what are you going to get? 2. And at 0? And that'll be over 3. So we get 6 over 3, or a zooming 2 meters per second. Now that is the slope of a secant line on this line. So if you think about it from